Hello, this is Dr. David A. Gaitros, Department of Computer Science at Florida State University, and I'd like to welcome you to my undergraduate lecture series on selected topics in computer science. You can find these videos and others at my YouTube channel at the URL listed below, or you can simply go to YouTube and search using Gaitros and FSU as keywords. Now on to the lecture.
Before we start talking about binary numbering systems, it's important that we understand our current system, decimal, or its proper name I suppose is base 10. Let's take the number 5,267. The little number 10 right here in the subscript tells us that this is a base 10 number. The base 10 number is based on 10 symbols. 0, I'm going to get my pen to work. There we go. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Alright, so those are the 10 symbols that we have, and that's why we call it the base 10 numbering system. Alright, well, let's look at 5,267. We just take for granted that that's what it's worth. In reality, it's a little more complex than that. So let's look at what it really is. It's really 5 times 10 to the third, okay, plus 2 times 10 to the second times 6 times 10 to the 1, and then finally 7 times 10 to the 0. Now, those of you who remember your algebra, any 10 raised to the power of 0 is always worth 1. So in reality, what is that? Well, that's 5 times, we'll write it over here, 5 times 1,000 plus 2 times 100 plus 6 times 10 plus 7 times 1, okay, or 5,000 plus 200 plus 60 plus 1, which is 5,267. Now, let's say that the 6 right here would have been a 0. Alright, well, it's still 0 times 10 to the first, which would have been 0, which would have been 5207. So this is how numbers are interpreted, and it's important that we understand this before we go on and look at the binary numbering system, because we're going to apply this same principle. Well, let's look at binary, and we'll just put the word binary up here. Binary. It has 2 symbols. It has 0 and it has 1. Now, the reason we use binary in computers is because of the simplicity. Inside a computer, inside a machine, the numbers 0 and 1 can be easily represented by off electricity or on electricity, or the presence of something magnetized or the presence of something not magnetized, or in punch cards, something is not punched or something is punched, a hole through it. So 0s and 1s are very easy to represent. And using 0s and 1s, we can represent any numbers. Let me show you. Let's say that we have the numbers 0, 1, 0, 1, and then 0, 0. Let's make it an 8-bit number. Let's just go ahead and put that 0 right there. So this is our binary number. Okay, well, how do we represent that? How do we know what decimal or base 10 number it is? And again, we're looking at whole counting numbers, or integers as we call them. Well, this first column right here is worth 2 to the 0, which is 1. This column is worth 2 to the 1, or 2. This one is worth 2 to the second power, or 4. 2 to the third, or 8. 2 to the fourth. 2 to the fifth. And of course 2 to the 6. 2, 3. Okay, let's add another one here. Let's make it 8 bits. 2 to the 7th. Alright. And then what we do is we find out anything that has a 1 in it, we add that together. So 2 to the third has a 1 in it, so that's worth 8. And then this one doesn't have it, but this one does. That's 2 to the first, that's 2. So that's 2. And of course, 8 plus 2 is 10. So this is equivalent to the decimal number or base 10 number, 10. Okay, very good. That's how you interpret it. And we'll look at that a little bit later. Okay. So when we put it into relationship of our decimal numbers, then what we have here is we have, let's say 1 0, 1 0, okay, is 1 times 2 to the third plus 0 times 2 to the second plus 1 times 2 to the first plus 0 times 2 to the zeros. This number right here is the base number, and this is the relative position. Starting count 0, 1, 2, 3, and you kind of get the idea. It just goes on out to infinity. Well, now then, next let's look at how we take a decimal number or a base 10 number and convert it into binary. Well, let me show you how to convert a number from base 10 decimal into binary. And the method I'm going to show you is the more formal method of the techniques. I'll show you another one later. It's done by dividing by 2. So I'm going to divide 2 into 5,267. And I'm looking to get the remainder. I'm going to put the remainders out here to the side. So 2 goes into 5,267, 2,633 times with a remainder of 1. So let's remember the remainder. Then we divide that by 2. And 2 goes into 2,633, 1,316 times, also with a remainder of 1. And I can almost anticipate the remainder just by looking at the rightmost digit. If I get a odd number, then I know that the remainder is always going to be 1. An even number will be 0. So this one will be 0. So we'll divide 2 into 1316. We'll get a remainder of 0. Likewise, we're going to divide 2 into 1316. We will get 658 with a remainder of 0. We'll divide 2 into 658 and we will get 399, okay, with a remainder of 0. 2 will go into 399, remainder of 1, it'll go in there 164 times. Let me get this 2 right here. 2 will go into 164 82 times with a remainder of 0. 2 will go into 82 times 41 times with a remainder of 0. It's an even number. 2 will go into 41. We'll say 20 with a remainder of 1. 2 will go into 2010 with a remainder of 0. 2 will go into 10 5 times with a remainder of 0. 2 will go into 5 times 2 times with a remainder of 1. 2 will go into 2 1 times with a remainder of 0. And finally, 2 will go into 1 0 times with a remainder of 1. And when we end up with a 0 here, we're done. This method ensures that we only produce the rightmost significant digits. Now to translate this, what you want to do is you want to envision that this is falling like a tree, like this over. Okay, so the digits are like this is the rightmost digit up here, and this is the leftmost. Okay, so the number that we're doing, number translating is 1 0 1, 2 zeros, a 1, 2 zeros, and a 1, 2 zeros, and a 1 1. Now, if you look at how these are translated, this is worth 1, 2, 16. This one was worth 128. This one was worth 1,024, and this was worth 496. Those should all add up to the decimal number 5,267. All right. Well, that is the formal method of doing this, and I'm going to show you one more here in just a second. Another method to convert a decimal into binary is kind of a brute force method, and if I didn't teach you any other way, this is probably how you would derive it yourself. It works well for small numbers, not very good for large numbers. It's a little tedious, but the division one can be tedious also. Well, let's say that we have a number, base 10 number, that we're using, and it is 155. We'll put the little 10 right there just so you know it's a base 10 number. So we want to convert this into binary. Well, up here what I have is I have the positions and their relative value. The first position to the 0 all the way to the 9th position, or to the 8th. And what we're going to do is we're going to convert this, and we're going to look at this up here and kind of put the 1s and 0s in the place where they should go. And it's done like this. I look at 155, and I'm looking for a number that is at 155 but not greater than. So here's 128 and there's 256. It's greater than 128 but less than 256, which means that I'm going to use this one right here, 128. And I take 128 and I subtract it, 128. Alright, so let's be careful about this. I'm going to subtract 8 from 5. Okay, so 15 carry. That's a 7. So that's a 4. That's a 2. So now it's 27. Very good. Now what I'm doing is I'm looking for a number that's 27, but between 27, at 27, but not greater than. So I don't see 27, but I see 32. That's larger. I see 16. So I'm going to use 16. I'm going to put one right there. So I'm going to subtract 16 from that, and I get 11. Okay. So now I'm looking for 11. I don't see it, but I see 8. So I'll use that. So I subtract 8 from it. Okay, and that gives me 3. Okay, I see 4. I see 2. I'll put a 1 right there. So I subtract 2, and then I see 1. So I'll replace it. I didn't put something, I put a 0. Okay, so I put 0 right here. So there is my number. Now let's make sure that works okay. So let's add up 128 plus 16 plus 8 plus 2 and 1. Alright, so 14, 16, so that's 5, and that's a 2, carry a 2, 4 and 5, and that's 155. Ah, it works. That's wonderful. Alright. Now, before we end this tutorial, I just kind of want to show you a few things in binary that are kind of handy to know. First of all is the numbers. Okay, 1010 is the decimal number 10. I remember that because it's 1010. It's easy to remember. But I also know that it's an even number, and I know it's an even number just strictly by looking at the rightmost digit. If the rightmost digit is a 0, then it's an even number. If the rightmost digit is 1, it's an odd number. Okay, let's look at 11, which is just really one more. Okay, so it's an odd number. Okay, now let's observe one more thing. Let's put 1010. Okay, and I'm going to add a 0 to the right. Okay, now what is that number? Well, this is worth 1, 2, 4, 8, and 16. 16 and 4 is 20. So we observe that if we shift the number to the left one digit, it's the same as multiplying times 2. Likewise, if we shift to the right, it's the same as dividing by 2. So let's take the number 10, 10, and let's shift it to the right. We have 101. This is worth 1, 2, 4. That's 4 plus 1, so that's 5. So Shifting right and shifting left is a shorthand for dividing and multiplication, which is used quite a bit in computers. Well, this is our lesson on converting binary numbers. I hope you enjoyed it and look forward to doing another one.